Professor Messersmith, you've contributed a great amount of pioneering work into the field of bioinspired surfaces. Could you tell us a little bit about your concepts behind these bioimitation strategies and their potential applications?
Sure. I think we have much to learn from nature in how to go about designing materials that can function in a variety of capacities. My own work is focused on wet adhesion, and so we look at organisms in nature that rely on adhesion to surfaces under wet environments, and we try to understand the concepts and chemical processes on a molecular level that give rise to their success in wet adhesion, and then we take that information and we use it to inform the design of synthetic approaches that hopefully capture wet adhesive properties, but in a synthetic material.
Mm-hmm. And what are some applications that you're mostly interested in?
Applications can range from coatings for preventing of fouling. Ironically, you can actually use these strategies to actually prevent things from attaching to surfaces like bacteria or cells or proteins. And then also in surgical adhesion. So in surgical procedures in the human body where you want to bond tissues together or a medical device tissue, the tissues are always wet, so you have a problem of adhesion to wet surfaces, which is a very difficult thing to do. So we like to think that the ideas from nature in wet adhesion can be implemented for surgical adhesion.
You showed in your lectures that there's an exquisite control of redox processes and perhaps some covalent, non-covalent interactions with materials that seem to have a diverse mixture of reactive groups. For example, DOPA is a natural amino acid, lysine is a natural amino acid. You put them together in all these proteins. And how does nature then control the fact that one species would like to oxidize to control adhesion, and yet we don't see cross-linking of our tissues with DOPAs, we don't see cross-linking of our intestines in a complex redox environment when we eat polyphenols. So how does all this chemistry work under redox conditions that are quite diverse in nature?
Well, this is trying to understand all this is one of the frontier areas of my field. So when I started this research 15 years ago, most of the activity was driven towards identifying these unusual proteins and also other components of the tissue which work in concert with the proteins to achieve certain mechanical properties. And in the case of the mussel adhesive proteins, all of these, there's at least 10 proteins roughly that are known and well understood in the structure in terms of composition, but how the organism mixes all of these proteins together into this complex tissue, which happens in about 2 to 3 minutes. It goes from a series of soluble proteins and mixes metal, redox active metals, with the proteins, and a series of chemical reactions, which we don't fully understand, occurs. You mentioned redox chemistry. So how the organism actually processes this into a tissue, all these ingredients into a tissue, and takes advantage of redox processes and pH, it controls the pH to presumably control the redox reactions. How it does all that is really the area where we need to learn more. So this is actually the frontier area of the field, which is trying to understand processing. So we've moved beyond the point where we need to learn about the proteins. Now what we don't know about is how does the organism put all those ingredients together in a processing mechanism.
So just to quickly end this, then, in ingesting polyphenols in red wines and chocolates, as you describe in your papers and your lectures, how does our gut, with its transit of huge amounts of redox and reductive capabilities, and then this enormous range of pH, how does our gut not, cross-link itself into oblivion just based on drinking green tea or red wine and eating chocolate, all the things we enjoy?
Sure. So first of all, don't believe everything you read about polyphenols in the media.
Including your paper. Oh, okay.
It's a very complex process when you ingest a polyphenol in a food or a beverage, and what happens to that compound. It's a very complicated thing. So the cardiovascular effects, anti-inflammatory effects that are often claimed for for these compounds. They may be real, but often they're very difficult to tease out from the data because it's very complicated what you put in your body, and then the cardiovascular or anti-cancer effects or whatever the biological output is. That's all complicated because the pathways are very complicated. So what happens to these compounds once they get inside your GI tract and then into your vasculature, who knows what happens. But circling back to the muscle adhesive proteins and DOPA, I believe actually there's a reason why DOPA is not found in human proteins, which is it's a very promiscuous redox active amino acid. So that usually is not a good thing in a protein. So the promiscuous activity in an amino acid goes against all of what we know and understand about specific biological interactions and reactions. And so this, I believe, is why DOPA is not found in humans, because it's just too indiscriminate in its chemistry.
Thank you.
Thank you.
Thank you.
Thanks.
That's awesome.